All right, everybody, nothing fancy going on in this one, just talking about tension and the pulley. And so specifically, this is usually referring to something called the Atwood machine. That's Atwood, Atwood. And it's named for Mr. Atwood. He was a famous procurer of, okay, it's all made up. Anyway, so here is what the Atwood machine looks like. It is a pulley, which I'm just drawing here as a circle, and I guess I'll put a little dot in the middle. And then on the one side, there is a mass. Okay, I don't know why that is popping up. Sorry. No edits going on this time. Just a straight shot. So we have a mass, say, on this side. Okay, fancy. Really not too far in. I probably could just start over, but I'm not gonna. I'm just gonna keep going. Okay, and then on the other side, we're gonna have something totally identical. So I move that over, duplicate, pull it over, and we have one of these things. All right. So the question then becomes, what's going to happen to these things? Which way are they going to move? How are they going to move? You probably, wouldn't be too far off with the guess that, well, it would have to do with whatever their mass is. And so we can give them masses by saying this is mass M1. We can say that this is mass M2. And then I can put a little note over here, and I can say maybe that M1 is greater than M2. Sometimes this is shown with a lowercase m and an uppercase m, where the uppercase is usually the larger mass, but there's lots of different ways to do it. And so this is just where we're starting now. Okay, so let's begin with a free body diagram of the situation right here. So we definitely have both of these having weight down, which instead of writing as FG, I'm going to write as M1G, and this one also has a weight down, which I will then write as M2G. And I'm not drawing these to scale right now. I don't really actually know how much bigger one is than the other. Right now I'm just saying that one is bigger than the other. When we're finished, we can say something about that. But for right now, we're just saying these are the directions. So both of those are being pulled down. And as a result of one of them being larger, it'll move in a particular direction. But right now I'm just interested in getting the direction of the forces correct. Now, part of this conversation is also about tension. So tension is a force that exists along a rope or a string or a wire or something of that nature. And it is the same throughout any wire, meaning that this rope is going around this pulley and attaching to the other side. And so the tension is the same everywhere, right, in this situation. So that the tension that this mass is experiencing is directed in this direction. This is what is resisting this mass from just falling to the earth with an acceleration of 9.8. All right, and we'll call it T2. All right, because it is associated with M2. The other thing that we could do, or that sometimes people will show like FT. It's just a force of tension, and this is reasonable to do when you only have one mass, which eventually we'll see some examples that deal with that. But it's not particularly useful to do it that way. So I almost always consider the force of tension to be a capital T, and then I can ascribe subscripts to indicate which one I'm actually talking about. Okay, now just like M2 is being resisted by tension 2, we can say that M1 is being resisted by tension 1. Now notice both of these are directing up. There's a kind of a pulling, a tautness to these situations, to this string. So both of these are experiencing this tension in this way, in this direction. Now, as I said before, the tension is the same everywhere on a single string. So what do I mean by that? What I mean is, if we had a situation where I don't know, maybe we had this same thing over here. All right, but let's not. Well, I guess I can leave that. And then I had an additional string hanging off. Okay, more complicated example for sure. But if I had an additional string hanging off, now if this string is just hanging here, you would, and we would call this tension 3. You would not expect this string that's attached to nothing below it would have the same tension as tension 1 and 2. Now, if we put a mass underneath it, you would not also expect right? If this is mass 3, you would not expect that tension 3 right here would be the same as tension 1 and tension 2. There is no reason for you to assume that, and because it's not true. The forces that are causing the tension in this string are different than the forces that are causing tension in these things. All right, so because this is a continuous rope or wire, the tension will be the same everywhere, all right, but obviously in opposite directions. And so, yeah, so there's that. Okay, so now we have to go on to figuring out how we are going to do it. And as I said earlier, these things are just going to get increasingly complicated. So good bookwork is going to be important. Just keeping track of everything that you are doing and talking about. So I'm just going to slide this over just a little bit. Because what I want to do is I want to be able to write the sum of the forces on for this system right here. But I have a problem. All right, because these two forces right here are really opposing each other. They're pointing in opposite directions of one another from their perspectives. And what do I mean by that? I mean, while they're both pulling down, right, from the perspective of 1, right, 2 is pulling it down. And from the perspective of 2, right, 1 is pulling it up. Right, they're opposites in that direction. So I mean, just to call down negative and up positive kind of makes it really difficult to figure out what's going on, because then it just seems like everything, you know, that's pointing down is negative and everything that's pointing up is positive, and that's not really how these things are interacting with one another. So we have to come up with a different way to do that, just a different way to visualize it or to make sense of it. And so here is my suggestion. This is not the only way to do this, but this is a way that works pretty well. So what I'm going to do is I'm going to imagine that I'm going to take this situation right here, and I'm going to lay it out flat. I'm going to pretend like this pulley isn't here. Or better yet, I'm going to pretend like I'm going to swing these masses up to the side so that they are in a straight line. So if I did that, it would look something like this. It would be a straight line, right? And here's my wire. And then I would have my two masses, okay, on either side. So I'd have M2 over here and M1 over here. Again, like I swung them up to the side. So like the circle would be, you know, right here. The pulley, I guess I should say, would be right here in the middle. All right, and now I'm going to sort of transcribe my free body diagram, where I'm going to say, all right, I have M2 moving, M2G as the force pulling it this way. Okay, and I have M1G, force of gravity, pulling it this way. Now we have a much better perspective on how these things are moving left and right. Okay, as in terms of left and right rather, instead of up and down. And this is a useful way for us to now put a direction associated with this. So because I know that this is going to be moving in the direction of M2, because M2 is the heavier mass, then I'm just going to go ahead and I'm going to call that the positive direction. That way, when I see this force right here, this is going to be a resistive force, right? It'll take away from this force, and I think that's what makes the most sense conceptually to me. So now I can also put in my tensions. Now you see, this is the typical way that all tensions are going to go, right? The tension on one is going to be the same as the tension on the other, all right? But they're just going to be pointing in opposite directions. All right, so that's a useful place for us to get to here at the moment. All right, now that I've done this, I can write some force summations for each block. I'm going to look at each block individually. Now, this is really the first time that we've had an example where we need to look at two objects and how they are interacting with each other. All right, so we have to have, you know, as I say, good bookkeeping. So what I'm going to write now, I'm not going to write like in the sum of the forces in the x or the y. Right now, I'm just going to put the sum of the forces on 1, like meaning the sum of the forces on block 1. So that would kind of be like the net force on block 1. But so I could write this as M1 A1 net. But the net is sort of implied because that is just how it's going to be moving. So I'm going to drop that net right there. All right, and then I'm going to continue on to the other side over here, and I'm going to take care of these two forces and their directions. So these two forces, right, I have negative M1G, which I guess I should write just for niceness. I'll write T1 first, because it's going to be pulling in this positive direction, right? It's pulling this way, and my positive direction is over here. All right, as positive. And my M1G is pulling in that negative direction, so I can then say minus M1G. And now notice that we are taking care of the directions, as we usually do, outside of the variables. All right, so whenever we substitute anything in, just make sure that you know that you're substituting in positive things. All right, so now I've written the sum of the forces on that first object. So I can do the same thing here. I can say the sum of the forces on object 2. Okay, and I take a look here up at object 2, and I take a look at the forces that I've drawn in my free body diagram, and I say, okay, well in this case I'm going to have M2A2, all right, and then I'm going to say the forces that are acting on those kinds of things. So what do I have? I have, whoop, didn't mean to zoom out. What do we got? We have negative T2. Okay, writing it in an awkward way, I guess. And then plus M2G. Okay, now, I have these situations to which they're all unknowns here, but depending upon what we were looking for, a typical thing that we would be wanting to find is they would say, what is the acceleration of the system? All right, right now we've just laid out like, hey, what do we understand about the system right now? So this is a good starting point for any of these types of problems. And these problems can and will certainly get more complicated than this, but for right now, this is just, hey, let's just analyze the system. What are some things that we know? What are some statements that we can make? One thing that I can say for sure is that this acceleration and this acceleration, they must be the same, right? This block here cannot accelerate more quickly than this block here. They are attached by this string. Now, some things about these strings that we're going to be talking about, just like when we first started talking about motion and all that kind of stuff, we said, hey, there's no friction, there's no air resistance, don't worry about any of it. Well, we're going to do something similar as we start to talk about tension. We're going to say all strings are weightless, massless, whatever, and they don't stretch or compress. They're perfect, all right? So they have no mass and they're not going to stretch. But either way, this mass cannot then move faster than this mass. With a faster rate, with a faster velocity, they have to always be doing the same thing, which means that I can come back over here and I can say, well, this isn't really A1, it's just A, because this one isn't A2, it's just A, because these two things, within the context of this greater problem, these two accelerations must be the same. Meaning, I am now beginning to relate these two equations to one another by some commonalities. Right? So some things that are the same. These two accelerations must be the same because they are connected by this string. Now, I also said, that these two tensions, because they're on the same thing, must be the same. Right? And then obviously this gravity must be the same. Okay? So just like we got rid of the T1 and, the 1 and the 2, with the acceleration, we can also say that these tensions, really, as we said, they're the same tensions everywhere. So even though it's related to mass 1 and mass 2, it means that I can get rid of this, and this, and this, and this. I can get rid of all of those subscripts because, as I said, they're the same. For the same reason that the accelerations, we're able to say those are the same, we can get rid of these little subscripts as well. So again, we're doing this to relate these to one another, because if I want to figure out how the system is moving, right, I can't do that without looking at the whole system, meaning looking at each individual object. Okay, and then in order to then look at each individual object and then look at the system, I have to relate those two equations, those two expressions to one another. So I have done that. What I have now, in that sense, is I have two equations and I have one unknown, right? So a thing that we're pretty familiar with at this point. So I need to solve for one and then substitute back into the other, and that whole thing. So let's go ahead and do that. And you can do it in whatever particular way you want, depending upon what you're looking for. It's obviously easier to do one thing than the other, or it makes more sense to do one thing over the other. But for right now, I'm going to take a look at this guy right here, because I can solve that for a positive tension, then I can substitute that back in. So I'm going to take this equation, right, and I'm going to move this version down here, okay, and then I'm going to do my algebra, and so I'll rewrite it as M1A plus, adding this M1G over to the other side, is equal to that tension. Okay, so now I can take this tension here and I can substitute it in back to this second equation into there. So I'll do that. So I will, just like I did, I might have gotten too much, but I'll duplicate that thing. Maybe. No, it doesn't want me to. Try again. Yeah, there it goes. All right, so I'll move this down here and get rid of that. And now I can take this business that I just highlighted, and I'll put it into this this tension, as I said I was going to. So I'll do it in, look, I'll move this, I'll just slide that over there. Now I need to get rid of this here, and again I am putting this portion, okay, oops, keep it the same. I'm putting that portion right in here, so you can see that that's where that's going. All right, and I'll make sure I still highlight it. Now I am not just putting that in there and just having that negative sign. This is in this parentheses here, which means we have to distribute that negative sign through. So I'll do that here on the next line. So now my next line is M2A. Hopefully you're following this math here. If not, you can rewind. Distributing that through, negative M1G plus M2G. Right, so we have all this. Now, a lot of things going on here. So if you are writing places left and right and scribbling in the margins of your, like you're going to have a real hard time with this. So make sure that you are being nice and neat and orderly as you go through these kinds of things. All right, now we are looking for the acceleration. Right, so keeping track of your 1s and 2s and all that kind of stuff going on. I can add this term here over to the other side to get the A's all on one side. So this now becomes M2A, right, plus M1A is going to be equal to, right, I move this term over, so now what's left over here is negative M1G plus M2G. So we're good with that. Now, I have an A in each one of these terms, which means I can pull that A out, and I can rewrite this as A times the quantity M2 plus M1 is equal to, I'm just going to rearrange these because I don't like having that negative sign floating out front. It's easy to miss, right, when terms aren't connected by that negative sign, so I prefer to write it as M2G minus M1G. Okay, slide this up a bit. All right, so now I can divide by this term right here, both sides, which gives me the acceleration here is equal to M2G minus M1G over M2 plus M1. I have to divide by that whole term, right? Because math. All right, now notice I also have a G and a G here, which means I can pull out a G out front of that if I want to as well. Oops, saying G, I started to write one. Which means this now looks like G times M, M2 minus M1 over M2 plus M1. All right, so I can write this, in an even fancier, not fancier, but just knowing that this G is a constant. And so what this ultimately says is like, well, if I have M2 minus M1 up here, and then I add them together down here, M2 plus M1 down here, and I multiply it by, all right, the acceleration due to gravity, I get my acceleration, which means we now have an equation for any Atwood machine ever as the difference between the two masses and the addition of them would give us that. Okay, so now if I were to say put some numbers, or I was just thinking back to this picture up here, let's say now that we have this, let's move it down. Okay, and take a look at it. Let's just say like that these two masses were now, I don't know. Let me just change this just so it looks a little different. Oops, that's not what I meant to do. Can change this so it just looks like, yeah, look at that. All right. So instead, let me get rid of this, and I can put an equal sign in here. What if they are equal to one another? What would that mean? Well, that would mean that in the numerator, this would be 0 because they're equal to one another. And they were equal. It doesn't really matter what's on the denominator here because this is 0, which means that this whole term here is 0, which means when we multiply times g, we get an acceleration equal to 0. So if they are equal to each other, you have an acceleration of 0. Does that make sense? Yeah, that does make sense. If these two masses are equal, they're not going to go anywhere. Okay? What if, instead, what if m1 equal to 1 and what do I want to do? I'm going to say m1 is equal to 1. No, this one, not that button. This button is equal to 1 and m2 is equal to 2. So if we were to substitute in those values, we would say, okay, it's g times m2, which is 2, minus 1, all right, and then you add them together on the bottom. We would say 2 plus 1. So that would mean that the acceleration here would be equal to g over 3, or 1/3 g, however you want to think about it. So now we have an answer. Okay, let me box it up. All right, we'll take a look at these in a more robust way. All right, but for right now, what you should try to do is the following problem. We'll say what is the acceleration? Can you find it? Okay, follow through that system. Worst case, right? You can come back up here because we already have the universal solution right here. That's what this is right here. This is the universal solution to this system. So if you don't know what to do, right, you can come to that answer and make sure you can use that to check. But give this problem a shot. All right.